fluid. So last day we have seen the cause of the viscosity. Cause of the viscosity, the two causes mainly we have talked about it. First cause was their intermolecular attraction force. Second cause was the molecular momentum transfer. In the case of the liquid, the most dominant feature is the intermolecular attraction forces is most dominant because the liquid, comparative to the gas, the liquid molecules are strongly bounded if you compare with it with the gas. That is why the attraction force is more. If you rise the temperature, the attraction force will be decreased and viscosity will also decrease. In case of the gas, there is a different phenomenon. In case of the gas, we have seen that if you increase the temperature, with the temperature, the viscosity also increases because due to the cause of the molecular momentum transfer. So last day we have seen the one derivation regarding this, and from the derivation we conclude some thing just before. So last day, and the derivation, if you remember the derivation that was written as the mu values. Mu of an ideal gas. What was that values? That has came the density, one correction factor, mean free path of the gas molecules into 8 RT. We're comparing this equation with the Newton's equation and we're getting these values. The dynamic viscosity of a gas, whether the gas is ideal gas, we are getting this. So if you increase the temperature, here you can see your viscosity of a gas is also increasing from the formula. You're getting it. Next thing is the consideration. That is the Reynolds number. One thing we are discussing in the viscous flow whenever it is coming, the Reynolds number. Just some concept I am giving it to you. Reynolds number, what does it mean by the Reynolds number? So Reynolds number is inertia force. Normally we are writing it like that, inertia force with respect to the viscous force for the case of the viscous fluid. So the order analysis, just we will see the order according to the order in the inertia force for a fluid, gas, or any substance. Inertia force, if you know this thing, that is mass into acceleration. That is the inertia force. So mass in terms of the order, if you're writing it, this inertia force. So mass, we can write density into volume, L cube, where L is the characteristics length. We are writing it previously, L is a characteristics. That means along the length, the fluid characteristics will be changing continuously. So that is the characteristics. Just like through a pipe, if any flow is occurring, then if you go the radial direction of the pipe, you will see the different position, different radial position, there is a different velocity. So each and every radial position, there is a different characteristics of the fluid, different velocity we're getting it. So that is right. And acceleration terms, we can write it down, the V dvds. So simply V for velocity, that is also another V. So we can be able to write it as V square by L. So V square by L. So rho L square V square is the inertia force. What about the viscous force? Viscous force is nothing but the shear force. Viscous force is nothing but the shear force. So shear force means shear stress into area. Stress, we can write it down, du by dy. If it is the Newtonian fluid. Newtonian fluid, I am coming later. Those fluid which are obeying the Newton's law of viscosity is known as the Newtonian fluid. Those does not obey non-Newtonian fluid. Just two classification. So let I think it is a Newtonian fluid. It obeys the Newton's laws of viscosity, and we are writing it here. So mu, if you in terms of the order, if you are writing it as a mu, this is nothing but the velocity. Du is the velocity, so v. Just in terms of order analysis, we are doing it. So u, v, the same. Only velocity. It is nothing but a velocity. And velocity order we are writing is the v. And y is along the direction. So that is also, you can write it by L, characteristics. Because if you go along y direction, the characteristics is changing. The flat plate you have seen, if you go along the y direction, each and every point having different velocity. And we have seen the velocity profile also there. And area is L square. So just for the order analysis, we'll see in the dimensional analysis chapter the order, how to get the order, but it's a simple example I'm giving it to you. So inertia force is getting is rho L square V square, viscous force is mu VL. So Reynolds number RE, we are writing it RE, the Reynolds number is nothing but rho L square V square by mu VL. So rho L V by, that is the Reynolds number. If you know what is the Reynolds number, we are writing it in the expression always like that. Rho, density of the fluid, velocity of the fluid, characteristics length of the fluid divided by the dynamic viscosity of the fluid. We're writing it. It is coming from the order analysis in this way. One chapter will come in your courses, that is the dimension analysis. We'll see the same things, just like in this way. Now the thing is, now we are going to in case of the ideal gas. So ideal gas, what is the Reynolds number is varying. So in case of the ideal gas, if your consideration is the ideal gas, your mu is rho attrition factor free path 8 RT by pi. And your Reynolds number, you can write it down. Rho V L by mu. So mu, if you put it here, just you put down the values of the mu. Rho will be cancelled out here. V, you write the V, and in below you segregate this term. Mean free path by L into alpha into 8 RT by. Here it is just like this way. Now if you divide it by this by A, where A is the sonic speed through the corresponding ideal gas medium. Sonic speed through the corresponding ideal gas medium. So the A, we can write it down from some equation gamma RT. A is equal to same gamma RT. So gamma R. So one just division and multiplication we have done it here. We multiply with the V with gamma T and divided by A. So V by A, this term, the V by A term will gives you Mach number, because actual velocity by sonic velocity will gives you the Mach number. In the bulk modulus topic, I have shown you this. This mean free path by the length will gives you the Knudsen number. And what is the remaining thing? Root RT will be cancelled out. Root RT and root RT. And so in that case, you can write it, able to write it that things is, that is the pi into gamma divided by 8. So pi is a constant, gamma is a constant, R is a constant, and this whole terms in a constant. So the Reynolds number into Knudsen number is equal to the Mach for the ideal gas you are getting. So Reynolds number into Knudsen number is equal to the Mach. So if the gas having high compressibility, high compressibility means Mach number is more than higher values, some higher values, more than one definitely. Above the supersonic, it may be much more higher. Knudsen number, if you have to continuity, if you have to validate the continuum hypothesis, if this medium is valid for the continuum hypothesis, so it should have been less than 0.01, less values, small values. So Knudsen number is not that much high. So to get the high compressibility, you must have to get high Reynolds number. Because if you want to get the high compressibility, high speed, you have to get the high Reynolds number. Then what does it mean if the Reynolds number is high? That means the flow will become turbulent. So for the case of the ideal gas, the high compressibility implies the high turbulence. That is a little deep fluid dynamics. I'm not going that much far, just give you some concept. This concept I will discuss it later. If you could be able to understand in the later stage also. Now we'll come to the rheological behavior of the fluid. The rheological behavior is such a science department where we are talking about the properties of the fluid. The rheological department, we are discussing about the properties of the fluid. If the fluid obey Newton's law of viscosity, if the those fluid obey Newton's law of viscosity, is named as the Newtonian fluid. So Newton's law of viscosity, what is telling? Tau is equal to mu du by d. Tau is equal to mu into du by dy. Those fluid those fluids do not so those fluid which do not obey Newton's law of viscosity, those are generally called non-Newtonian fluid. So Newtonian fluid is a linear relationship. This tau is the shear stress, and this is the rate of angular deformation, we can say, or shear strain rate. Rate of shear strain. So shear stress and shear strain rate is a linear relationship. And considering mu is a constant values. Mu is a constant. Newtonian. Example of the Newtonian fluid. Water we are considering as a Newtonian fluid. Air, diesel, etc. This all of the Newtonian fluids. Non-Newtonian fluid having some divisions, because this fluid does not obey the relation. This relation, tau is equal to mu into du du. Hence,